Hi, in this video we are going to discuss the linearity property of the Fourier transform. That is, the Fourier transform is a linear operator acting on signals. Or in other words, if you have a linear combination of some signals, the Fourier transform of the linear combination is the same linear combination of the Fourier transforms. Now let us express this in terms of two signals. We have x1 of t with the Fourier transform x1 of omega. x2 of t has the Fourier transform x2 of omega. Then alpha 1 x1 of t plus alpha 2 x2 of t will have the Fourier transform alpha 1 x1 of omega plus alpha 2 x2 of omega, where alpha 1 and alpha 2 are constants. Now, for real valued signals, the constants are chosen as real valued. For complex value signals, the constants are chosen as complex valued constants. Proof of this result is very straightforward. In fact, the Fourier transform of alpha 1 x1 of t plus alpha 2 x2 of t is, we can use the definition of the Fourier transform in terms of the Fourier integral. The integral of alpha 1 x1 of t plus alpha 2 x2 of t multiplied by e to minus j omega t integrated with respect to t. Now, using the fact that integration is a linear operation, using the fact that integration is a linear operation, this integral can be decomposed as alpha 1 from minus infinity to plus infinity x1 of t e to minus j omega t integrated with respect to t plus alpha 2 from, again, minus infinity to plus infinity x2 of t e to minus j omega t integrated with respect to t. But as we see, this integral expression is capital X1 of omega, and this expression here is capital X2 of omega. So this proves that if you try to obtain the Fourier transform of a linear combination of two signals, the Fourier transform of this linear combination is the same linear combination of the corresponding Fourier transforms. Now remember, these terms, linear combination of vectors, functions, etc., or the term linearity itself is closely related to the algebraic structure known as vector space. So we are in fact discussing the linearity of the Fourier transform in the following sense. The Fourier transform is a linear operator from the vector space of functions which are called signals, which are Fourier transformable, to the vector space of the set of Fourier transforms of these signals. So in a more general sense, linearity is interpreted as the structure preserving transformation in the context of vector spaces. Okay, now let us see an example. Now this property of the Fourier transform, the linearity property, is quite easy to understand, but it has extensive applications because in many cases we have an expression which is in the form of a linear combination of signals. That means signals multiplied by constants and then added. The two operations in the vector space, addition and scalar multiplication. Okay, so as an example, let us first remember how we calculate the Fourier transform of an exponential signal. Let me call it x cap of t as e to alpha t u of t. Now we have considered this example before, but we didn't consider the case where alpha is complex. Now let alpha be a complex constant such that its real part is negative. Because we want an absolutely integrable signal. So we have to impose that condition. Real part of alpha is negative. So we have a decaying exponential. In other words, alpha is alpha r plus j alpha I, where alpha r is the real part and alpha I is the imaginary part. We have no restriction on the imaginary part because the imaginary part will give rise to sinusoidal oscillations. So the important part is the real part. The real part must be negative, so we have a decaying exponential, and therefore we have the condition of absolute integrability satisfied. So we have capital X cap of omega equal to, from minus infinity to plus infinity, e to alpha t u of t e to minus j omega t integrated with respect to t. So we have from 0 to infinity, because u of t is 0 for negative values of t. So from 0 to infinity we have e to alpha minus j omega t integrated with respect to t. Now since real part of alpha is negative, this signal is absolutely integrable. The signal, original signal, x cap of t is absolutely integrable. Therefore, the Fourier transform will exist, and this is equal to 1 over alpha minus j omega e to alpha minus j omega t evaluated at 0 and infinity Now, as t tends to infinity, this term will decay to 0. Why? Because real part of alpha is negative. Therefore, we have a decaying exponential, and the result will be 0 in that case. So, we have x cap of omega equal to 1 over, with a minus sign, minus 1 over alpha minus j omega, or 1 over j omega minus alpha. Here alpha is the complex constant, but the important point is that it is not an arbitrary complex constant. Its real part must be negative to satisfy the condition that the signal is absolutely integrable and the Fourier transform exists. Now let us consider now the signal x of t equal to e to minus t cosine t u of t. Now x of t is obviously absolutely integrable because magnitude of x of t is e to minus t times magnitude of cosine t. Cosine t is always bounded in magnitude between minus 1 and plus 1. So its magnitude is less than or equal to 1. Therefore, the Fourier transform of this signal exists. But also, we see that x of t can be written in the following form. It is e to minus t, then we have the cosine, which is e to jt plus e to minus jt divided by 2 u of t. So this therefore can be written as 1 over 2 e to minus 1 plus j t plus 1 over 2. Let me also write u of t here. U of t plus 1 over 2 e to minus 1 minus j t u of t. Now, by using linearity of the Fourier transform, we can use the Fourier transform of x cap of t, which is capital X cap of omega, to obtain the Fourier transform directly. So by using linearity, x of omega is equal to 1 over 2, 1 over j omega minus, now alpha here is minus 1 minus j, plus 1 over 2, 1 over j omega. For the second term, we have a similar reasoning. We are using the linearity of the Fourier transform because we have now a linear combination of two exponential signals with complex exponents, j omega minus, again minus 1. For the first one, we have minus 1 plus j. For the second one, we have minus 1 minus j. Okay, this expression can be further simplified by combining these terms and with some algebraic operations, this expression can be further simplified. But essentially, the important point here is that first we have obtained the Fourier transform of a of an exponential signal with a complex exponent, alpha, in the exponent of the exponential term. And we have the restriction that the real part of that alpha, constant alpha, must be negative, so that we have a decaying exponential. Because of the imaginary part of alpha, we have the sinusoidal oscillations, but they do not create any problem in the convergence of the integral, since they are just sinusoidal terms which are always bounded in magnitude. So the important term is the real part of alpha. So after calculating the Fourier transform of this signal, now we can apply it to our signal x of t, which can be written as the linear combination of two such complex exponential signals, and we are able to calculate the Fourier transform in a straightforward way by using the linearity property of the Fourier transform. Thanks for watching.